All right, let's talk about one of the most fundamental ideas in AI search. Whenever an AI needs to find a solution to a problem, it faces this big choice. Should it dive deep down a single path, hoping it's the right one, or should it carefully check all its options, level by level? It's the classic showdown, going deep versus going wide.
So think about it. How does an AI actually find that needle in a haystack? You've got this, rational agent, and it needs to find one specific goal in a huge, tangled web of possibilities. It can't just wander around randomly, right? It'd get lost forever. It needs a plan, a system, a search strategy to figure out where to look next.
So here's how we're going to break it all down. First, we'll nail down what the search problem actually is. Then, we'll dig into our two big strategies, depth-first search, or DFS, and breadth-first search, BFS. After that, we'll throw them in the ring for a head-to-head showdown, and then wrap up with the big takeaway.
Okay, so what is the search problem, really? Well, at its heart, it's pretty simple. You've got an agent at a starting point, we'll call it S, and it's got to find a path to the goal, G. But here's the catch. The agent is basically flying blind. It has no map, no GPS, no idea how close or far the goal is. It just has to start exploring.
Now, to keep itself from going in circles, the agent keeps this running to-do list of all the paths it's found but hasn't gone down yet. In the world of AI, this list is called the fringe. And honestly, the entire strategy, the secret sauce for every search algorithm, is just the simple rule for how it adds paths to this list and which one it decides to explore next.
Let's dive into our first strategy, depth-first search. And as you can probably guess from the name, this one is all about taking the plunge and going deep, fast.
The rule for DFS is super simple. Always explore the deepest path you can. It picks one direction and it just goes. It digs deeper and deeper and deeper down that one rabbit hole until it either hits a dead end or, fingers crossed, finds the goal. Only then does it backtrack and try another path.
So how does it pull this off? What's the secret engine making this deepest first strategy actually work? Well, it all comes down to a data structure called a stack. A stack works on a principle called last in, first out, or LIFO. Just imagine a stack of books on your desk. The last book you put on top is going to be the first one you grab, right? It's the same thing here. Every new path the agent finds gets pushed onto the top of the stack. And when it's time to pick the next path, it just pops the newest one right off the top. That's what naturally sends it deeper and deeper down one single path.
So how does it stack up? Let's look at the report card. First up, completeness. Will it for sure find an answer if there is one? Yes, but with a catch. We have to make sure it doesn't get stuck in an infinite loop. Okay, how about optimality? Will it find the best answer? The shortest one? Nope, absolutely not. It might find some crazy long roundabout path just because it happened to stumble on it first. But this is where DFS really shines. Look at that space complexity. Because it only has to remember the one path it's currently on, it is incredibly memory efficient. It travels light.
All right, so that was going deep. Now let's completely switch gears and talk about going wide. Let's meet our second strategy, breadth-first search, or BFS.
The strategy here is the exact opposite of DFS. BFS explores the shallowest, closest options first. Instead of taking a deep dive, it first checks all of its immediate neighbors just one step away. Then it checks all of their neighbors 2 steps away. It spreads out from the start in these careful, ever-widening waves, kind of like ripples in a pond.
And the engine that powers this super methodical, level-by-level exploration, it's a different kind of data structure, a queue. A queue runs on a first in, first out, or FIFO principle. Just think of a line at the grocery store. First one in line is the first one to get checked out. It's the same idea. New paths get added to the back of the queue, and the agent always works on the path at the very front, the one that's been waiting there the longest. This guarantees that it explores all the nodes at depth 1 before it even touches a node at depth 2.
And what does that get us? Well, BFS is complete. Yep, it will always find a solution. And it's optimal. It is guaranteed to find the absolute shortest path to the goal. That's huge. But there is a massive trade-off. Take a look at that space complexity. To make that shortest path guarantee, it has to keep track of every single path at every single level. The memory it needs can just explode exponentially. As one source put it, it can get very scary, very fast. This thing's a memory hog.
But even with those crazy memory demands, that guarantee of finding the shortest path makes BFS incredibly powerful. It's the core logic that powers things you use every day, like your GPS finding the quickest route,
or a Google web crawler mapping out the internet one link at a time.
Okay, we've met the fighters. Now it's time for the showdown. Let's put depth first and breadth first search right next to each other and see how they really compare.
You know, it really all boils down to their engine rooms. DFS uses that last in, first out stack, always grabbing the newest, deepest path it just found. Meanwhile, BFS uses that first in, first out queue, patiently processing the oldest path first. This one tiny difference in how they manage their to-do list creates two wildly different behaviors.
And this table just lays it all out, clear as day. Look at optimality. BFS gets the gold star. It says, yes, I'll find the best path. DFS says, nope, not my job. But then look at space complexity. DFS is lean, mean, and efficient. BFS is an absolute monster that can eat up all your memory. And that's the core conflict, right? Do you want the guaranteed best answer, even if it costs a fortune in memory? Or do you want an answer, right now, with very little overhead? There's no single best algorithm here. It all depends on what you're trying to do.
So after all that, what's the bottom line? How do you know when to pick which one? Let's nail down the final takeaway.
I love this quote because it just nails the central tension. That memory requirement for BFS can be genuinely terrifying on big problems, but you just can't argue with the results. It's fast and it guarantees you get the best solution.
So here's the rule of thumb. You choose DFS when your memory is tight and you just need to find an answer, any answer, and you need it fast. You don't care if it's the best one. But you choose BFS when the absolute shortest path is what matters most, and you've got the memory to burn to find it. It really is that simple. One goes deep, the other goes wide.
So I'll leave you with this final thought. If you were building the next Waze or Google Maps, and your whole job was to find the shortest, quickest route for a user, what strategy are you going to choose? Are you going to risk going deep with DFS, potentially sending someone on a wild goose chase down a long, winding country road? Or are you going to go wide with BFS, systematically checking every option to guarantee you find the absolute best path?